That's going. So everyone can see what I'm doing, more or less. You may have to, if you've never used Discord before, when you click on the voice channel, you have to click on the person who's casting, because multiple people can cast at once. So you pick the person you want to watch. Let me drop a link. Dominoes. So I put together a tiny project, which I don't think we can from scratch cover the whole thing, but in terms of like just getting an idea of kind of the project structure in Unity and some of the basic stuff for Git, I will drop this link in the channel chat. Or actually, so yeah. Roll. If you go to this link, this is something, so Git is a program that just runs on your computer. You can run it anywhere. And Git works by storing code changes, sort of snapshots of a project in something called a repository. And GitHub is not the same thing as Git. So GitHub is like a big cloud server where you can store repositories and do a bunch of other stuff, but it's not actually the same as Git. So GitHub is a company and Git is a piece of software that's open. So if you want, we're not going to do this, but if you wanted to, you could clone something from GitHub and then store it in a different service like GitLab or Bitbucket. There's all these different, or GitKraken. There's a whole bunch of them that are these repositories. Oh, is that like source tree? Is it? But it's better than source tree, right? Yeah. Okay. I can. I will show you. So source tree is when Git is confusing because it's a lot of command line stuff that is hard to memorize. So sometimes what people use is they'll use a graphical user interface, a Git GUI like source tree or GitKraken. And so like there was a game jam like a month ago that I was working with some people on, and you can see here there's all these nodes. So the nodes are commits. Every time you make a change to your project, when you make a bunch of changes, what you do is you tell Git to track the changes. So here's all the things I changed. I want you to pay attention to them. And then Git will save it. And what it does is with text files, at least, when you've ever used like Microsoft Word or Google Docs, there's tracking changes. It literally just looks at where the letters. And so instead of storing a complete copy of your project every commit, it stores the delta every commit. And so like in source tree right here, you can see all of these messages are commits. So there are changes between, and then this thing here, GGJ deadline, it's called a tag. So in Git there are commits, and then that's kind of like the atomic unit of stuff. But then there's special kinds of commits called branches, and there's commits called tags. And basically, the way when multiple people are working on a project, if they're touching the same files at the same time, they can get what's called a conflict. So if I change files in a certain way, you change files in a certain way, change them at the same time, like in the same, if commits are like time steps, if people change things at the same time step, then the program doesn't know which changes to take and which to not take. What people do is they bifurcate the project, they make two branches, and then they have diverging commit history. And then when they're ready, when all their changes are done, they will merge them back together. But the diverging histories, what you do is find an example. So like over here, can you guys see that there's blue and yellow and green? And so the thing on the far left is the main branch or the master branch. And it's kind of like a tree trunk. So you have the tree trunk and then these tiny branches sprout off. And then what happens though, it's weird, it's like a hyperbolic tree because the branches bend back into the trunk, which is very strange. But when, so it's like, yep. Um, and you can see when a new branch gets made, like there's a blue node and then a red branch comes out of it, or there's an orange node and that goes back into the blue. And so there's all these relationships where people are what is the, I should probably, but it won't be stored here. I have an iPad I could draw on recording, but um it's literally, repositories are maybe okay, I don't need to draw it because I can Google it. These sorts of diagrams are really helpful because they it kind of matches up the command line stuff with conceptually what's going on. But basically, a branch and a tag, those are just names that you give to a commit ID. And so when I say that I am on a branch, I just mean that all the work that I'm doing is relative to this snapshot of the project. And so when people are on different branches, they're on different project snapshots. And the reason why branches are useful is because instead of being fixed to one commit ID, as the project moves, the snapshot that the branch points to can change. So that's why you'll have the node and then the divergence. So the two branches might point to the same node, but then they split and now they're pointing at different nodes. So because like what happens is you do something called a checkout. So there's a change up in the cloud, and you take that node, you take that commit, that version of the project, you check that out, and then what you do is you mark it as, I want a branch for me, because there's the main branch, but you want your branch to make your work. I'm going to do my work relative to this commit. But then you commit a change, you make a change. You're no longer on that commit. You've made a new change, so you've forked. Or not, well, forking is something else, but that if you imagine the main branch is going like this. Yes.
Like, so this main branch.
Yes.
You like create.
Yes.
Then you want to fit it like where the.
You pull exactly. Yeah. So that's called, you have to synchronize your changes with but that's the thing. Once so we've covered diverging. So once you're off, oh, thank you. Or yes. Oh, cool. Yeah. So this is like a regular project, and there is, well, actually I have an iPad. I have an iPad too. I can, that way you can keep yours. Just for the people who are watching the recording later, it's confusing, but and I also don't want to take too much time for Git because we should get to Unity also. But if you imagine, so this is the initial commit in the project. That's the base file. And then somebody, a single developer, he makes changes, he or she makes changes. And they've made a couple of changes. And so developer number 1 is over here. But then developer number 2 comes. And at this point in the project's history, this is all there is. So 2 starts over here. But then 2 makes a change on their branch. Their branch is now over here. And the 2 moves. The marker, a branch is just a floating label. So it goes over there. But if you want, it's arbitrary. If number 2 want, you can do something called git reset, which lets you go backwards and throw stuff out. So if 2 wants, they can go 1 back, 2 back, 3 back. The branch is just a marker telling you which snapshot of the project your features are relative to. And so what happens is the guy on number 1, he's going to keep doing his work. And then at some point, he'll make breaking changes and he wants number 2 to update. So number 2 will also have done work. They're over here, but now what this is the main branch over here. This is number 2's branch. Number 2 is now 1, 2, 3 commits behind number 1. So what they have to do is they have to pull. So a pull in Git is actually 2 steps. Number 2 doesn't know that this exists yet. So they have to fetch those changes. Once they've fetched the changes and they know that it exists, they can decide to merge. There's also something called a rebase. That is more complicated and a slightly different approach to Git commit history. Merging is the easiest thing to do. So what they do is but basically you can kind of imagine that they fetch the change. Now it's kind of like temporary. They say, okay, I'm ready to combine to resolve the differences. And what they do is they merge. And now, if they want, this is where it gets confusing with the collaborative stuff. Now number 2 is up to speed with number 1. But number 1 doesn't have any of the work that number 2 made. Right. So now in 2 has the changes from 1. So 2 is synchronized, but 1 isn't synchronized yet. So now what 1 has to do is they have to make another merge, which in GitHub is what's called a pull request. So once 2 is synchronized, what 2 says is they don't have the privileges to commit to the main branch. So they have to ask number 1. They say, developer number 1, I have synchronized your changes and merged them with mine. Can you put them into the main project? Can you make them permanent as part of the, when you go to GitHub and you clone something, the default thing you clone is main. So in terms of like the project lifecycle, your work is like part of the project once it's in the main. It used to be called master and they switched it. Some people, there's master, main, production, dev, there's all these different names, but we're gonna call them main. So the way before GitHub, all you would literally call number 1 up on the phone, send him an email saying, please fetch and merge my changes. GitHub lets you automate that process using something called a pull request, which is in GitHub, you go and you click the button. Instead of sending the email or the text message or whatever, you just click the button in GitHub. And then there's this nice little window where you get to decide that you want to accept. So if the workflow is in GitHub, I ask you to review my changes. You can approve my changes. And once they're approved, you make the merge. That's the pull request cycle. So what happens is now this is going to go here. And we have the final bit. And what's happened now is everybody, now the branch labels are on the same committee. So that's a very convoluted, but that's what's important, is to sort of visualize you have the main branch progressing forward. And you have feature branches or developer branches, and they go off, and then they have to synchronize, and then they go back on. So you get these loops. As a project advances forward, if you have a dozen developers, you'll have a dozen loops at any one time. And the thing is, if there's like a third developer, what he can actually do is he can have loops with the second developer. So you can have like subtrees. So what you'll have is, in something called trunk-based development, you have the big trunk, that's where everything is permanent, and you have what are called feature branches. So if I'm making a video game and I want somebody who's responsible for the camera, somebody is responsible for the graphics, somebody is responsible for the sound. Those are 3 different features. But maybe it's not somebody, maybe it's a department of people. Maybe there are 3 or 4 people responsible for the sound. So there's a branch for the sound, and then there are sub branches for every individual developer. So when you are doing your work, likely if you're organized about it, you'll have a branch that's named after you, and then you'll have the feature branch that you're working relative to. And once all of you finish your feature, the feature is what gets merged into the trunk. Yeah. Yeah. Yes. So pull is 2 things. There's another concept, which is, this diagram is also good. These are both good diagrams, but it's confusing. So there's this, see this dotted line between the local repo and the remote repo? So this is the part of Git that can get really confusing because you have your local commit history, local snapshots, and then you have the definitive version up in the cloud that everybody shares. So not only is there synchronizing between branches, there's synchronizing between what are called remotes. So there's the local version and the remote version of the same repository. And you can have multiple remotes, which is where things get really confusing. So for our projects, we just have one. It's called origin. So when you, in your command line, work with Git, you'll do something like git pull origin main. What that says is, get me all the changes from this remote on the main branch. And if you remember, the branch is the commit ID, so it tells you which snapshot. Origin tells you the URL. Where on the internet does the snapshot live? So git pull origin main is, get me this commit ID from this URL and put it on my hard drive.
So then if we're working on floor city.
Yes, yeah. Exactly. And then what you would do is, you never work directly on the branch that you are a sub branch of. So what you would actually do is you would, so this is where the git pull and the git check, so it's actually something called a checkout. So pull is for synchronize. If it's your first time cloning the branch, you do what's called a checkout. So you would check out city, and then you would make your feature branch. So you would do check out the city, and you do make a branch called music. And now you're making music relative to city, which is relative to the whole big project.
So that exactly music, yeah, branch.
So that's where it's also confusing because you can have everything. So just think of it as one big Git project is the version of the repository on the cloud and the version of the repository on your hard drive. They are not necessarily the same. So just like with the commits, you have to synchronize the branches. So when you make a branch locally, it'll live on your hard drive, but you have to tell the cloud about it. You have to tell the remote about it. So that's where it's called setting an upstream, which is, there's so many words. There's just so many words. But so like, if you look at this diagram, let's see, does it have, okay, the Git data transport. So you have your remote and you pull your changes, but then you have to add, commit, and push your changes. And it's in the push step, that's when you specify the branch that you're pushing changes to. So if your branch doesn't exist yet, there's a shortcut, which is git push -u, and then your branch. And that will take your local branch and make it exist remotely. -u is an abbreviation for something called set upstream. So all of your local branches have an upstream equivalent. So what happens is when you make a branch locally, you create an identical copy in the upstream, and then you synchronize them. So your local branch tracks the upstream. And all that means is because if you remember how the branch is like this floating label for a node, when the position of the label changes in the upstream, when you synchronize, the position of the label on your hard drive also changes. You're good. No, yeah, no, take your time. Git is a very powerful tool, but it's also exceedingly convoluted and confusing. So what we're gonna do, so now we've talked about push, kind of. So what I'm gonna do is actually just show you how this works, like in practice, because just talking about it is a lot. Yes. Yes. So the pull is so merge is a local operation. So two local branches need to be merged. You cannot merge with the remote because it lives up in the sky and it's not on your hard drive. So merge operates on data that lives in the same place. So in order to operate on data that's in the cloud, first you have to put it on your hard drive. So you pull it, well, you fetch it. You fetch it and then you merge it. But because it's redundant and you do it so often, they put the two together. It's behind the scenes, it's a fetch and a merge.
Oh, okay.
But it's called a pull. The pull is like an abbreviation for those. And then the reciprocal of a pull is a push. That's just you put your branches and changes and all that in it. And then rebasing is this thing where when you merge, you have merging. If you imagine my fingers as nodes, this merging will do this, which is good, but then chronologically you'll get features intermingling. So some people prefer to do something called a rebase, which is where instead of sticking your fingers together, this preserves all the nodes, but they're jumbled. In a rebase, what you do is you stack them. And now you don't have a chronological commit history, but you have a semantically coherent commit. But that's a stylistic thing. A project of this scale doesn't matter. So the simpler thing is to just merge. That's the easiest thing to get your head around. Before I show the actual thing, any questions? All good? Okay, so going back here, if you're on GitHub, here's the...
One quick
yes,
I'm
yeah.
sorry. But if you merge it, would that branch disappear?
No, so that's the thing. Every time that you can still see, you have to manually go through and clean up your, so that's like if you accept a pull request on GitHub, backend, yeah, the label still exists. Huge, yes, yeah, because you'll have dozens of people with their own branches. So what happens is you'll often keep the branch on your hard drive, but up in the cloud, it'll get archived. So it's in an archive, so you can still go back and see it, but it's not under an active branch.
Merging it, try and make another branch to like...
Yes. Every time a feature is merged, when you start a new feature, new branch. One feature, one branch. All right. So this is GitHub, and this over here, you guys can see, I think, so main, this is like, right now there's just one branch. That's fine for now. The most important thing is if you click this green button that says code. So the old way of doing stuff was you would use HTTPS, which is, there's just different protocols for downloading files. SSH is preferred. It's also a little more complicated to set up because you need something called an SSH key. I'll show you how to do that, but when you do this on your own, if you don't have an SSH key set up, just use HTTPS, and what you do is you enter your password in the terminal, which is a little bit, the reason people don't like that is because it's not as secure as using a key. But what they mean by keys is in the settings, you have actually this list. And these are cryptographic keys. So what happens is when you make changes to a repository, you sign them with your cryptographic key and you upload them. What GitHub knows, because GitHub has your public key, can verify that the changes you're making are coming from you. It's more secure than just using a password to authorize something, because the changes themselves are signed with your key. The generating SSH key guy, that's like a whole other messy, there's lots of different ways to do it. For now, just use the HTTP. But I will show you. So what you do, if it's HTTP either way, you just copy the URL, and then in your terminal, what I do is you guys know how to use terminals, sort of? Okay, it's like changing directories and making directory. Okay. Yeah, so what I like to do is I will actually just make a folder called code in my root. And I'll have things like Python assignments and all that crap. But for Git, what I do is I have a subdirectory called Git. Like some of this stuff here is like the repository from last semester. What you do though is in terminal, you just go into that. And yeah, that's the right place. So what you say is you say git clone, and then you paste that URL that you got from the website. So you can see that this is an SSH request because it's giving the user Git and the domain GitHub and then the address of the repository. So repositories have a .git extension. You hit enter. Now I have to give a password for my key, and I don't remember what it is. Nope. There we go. So now it cloned the project. The thing about this project is if you go inside of it, you will see that there's something called, oh, these are hidden files. I don't know how to actually show hidden files on a Mac because I use Windows for a long time. We're getting used to Mac. But once you've done the clone, it doesn't automatically put you inside that folder. So you have to change directory, go to the thing, and now you'll see that if you've got an intelligent terminal, it will tell you that you're on the main branch. It recognizes you're in a Git repository. It tells you the branch you're on. If you list all the files, if I go into base project is what we'll be working with. There's something called a .gitignore, ls-a. Gitignore is important. So if we look at that, the thing about Git is not all of the information in your project is necessary for synchronization with the cloud, because a lot of it is auto-generated by Unity on the fly, and it will be deterministically generated. So even if it's not stored, it'll get generated the same way every single time. So it's redundant and uses bandwidth to stick that in your repository. So what we do is the gitignore file lets you just tell Git, please don't track these ever. So things like the build folder, that's good not to track because binaries are huge and Git isn't good at dealing with binaries. Something called meta files, those are really important. Never ignore them. The gitignore can tell you what to ignore. It can also tell you what never to ignore. Meta files are important because Unity has an internal asset database that it uses to synchronize everything. The meta files are the metadata that link assets like textures and models and code to things in the database. And one of the biggest sources of merge conflicts with Unity projects is when different people have different versions of meta files and then they keep kind of going back and forth with meta versions. So, but hopefully we maybe will have an example of resolving a merge conflict. I'm not sure. But yeah, so these are all just things that you don't need to keep track of. This is something called Vim, which is like a terminal-based text editor. There's also VI, there's like Nano, there's Emacs. It does not matter. The thing to know with Vim is when you want to do something, you hit colon, and now you have commands. I can hit Q, quit, and I leave. So a lot of people to open up Vim and they get stuck because they're like, how do I get out of this? And it's just escape, colon, Q, you're gone. If you want to save it, you do right, quit, WQ, you're gone. Now that we've done that, we can actually open this. The one thing I remembered, this is saved with Unity version, I think this is 2021.2, unfortunately, point 11. That's okay though. So as long as it's a minor version, like don't do this often, but if you're like a minor version off, you can go back. So just for this example, it's fine to, the next time I'll have it in 0.9. And for the main project, you should make sure you're doing it in 0.9. But for right now, it's okay to be on 0.11. So you guys should still be able to open this. But when you clone a project for the first time, it's not actually going to live. Unity Hub doesn't know about it yet. So what you have to do is you go to Add Project from Disk. And it's right there, Unity 101 Asteroids. But Unity 101 Asteroids is actually gonna have a couple different project versions. So I've actually put the Unity base project as a subfolder. So click on the subfolder and do Add Project. And now we can open it. And it will take a moment. No. Sorry. Yeah. Glad to hear it. Good luck with the meeting. Yeah, I know. It's always with the Discord. Discord's great, but it's different when you actually. Yeah.
There we go.
Bye, everyone.
Bye. There's another one. Oh my god. Okay, so they've already put out Unity 21.2.12. Wonderful.
I wish.
It is version.
After
Yeah.
20.
Right. 2020 is pretty stable. The thing I find, the minor fixes, what's a problem when you move between like 2021, 2019, like all that, you can get problems. But if you're moving between minor fixes, the newer ones, like when you go from 0.11 to 0.12, they actually usually make. So one of the things, like on my own, whenever there's a new version, if it's a minor version, I'll update. If it's a major version, I hold off. But if it's a club and there's lots of people, it's helpful just to lock it, because then you don't have to waste all the time downloading gigabytes of program files. So anyway, now we're in Unity. We did it. And have you guys ever opened? Is this your first time seeing a Unity project? Have you sort of okay? So then, so the good thing to know is there's something called a hierarchy, there's something called an inspector, and there's something called a scene view. So a scene is like this data format where all your stuff lives. So like not a good example. So like here's the scene with the main game, and it's just this little capsule, and it does some stuff on the camera. Scenes are where you put all of your objects that make up your game. So Unity uses something called game objects as a sort of the unit of not of logic, but of like semantic collection. So if I have a character, the character will be a game object. But the individual pieces of the character might be composed of lots of different scripts. So if I look at this player over here, you'll see that they have a mesh renderer component, they have a capsule component, they have some collider components, and then they have this important thing called the player controller, which is something that I wrote. So Unity uses something called an entity component system. That can mean different things in different contexts. Unity actually is two different kinds of entity components. One of them is very buggy, and one of them is this. But all that means is that the semantic objects in your game, a cat, a dog, a house, like all those things will be made up of lots of different like Lego bricks. Like in Lego, you build a house out of bricks, but the bricks are different. But your house might be different from another house, but they could share bricks, basically. So you can reuse components between objects. That's all. So entities are composed out of components. That's all entity components. Sorry? You're fine. So here in the scene, you can see that we've got our guy, and then if I hit the play button, that takes me from the scene view into the game view. And game view is like, this is a simulation of what someone running their program on like your program on like their phone or their Xbox would see. That's how you test your game. So this is just for like a demo project. It's just a little like spaceship thing that rolls around and tumbles, all that. So like asteroids, if you've ever heard of that game, like stuff. It's a very simple thing to implement. The thing to know about scenes is that you can switch between them. So like here's a start menu. And if you look on the left in the hierarchy, so the hierarchy tells you what's in your scene. So list of all the objects, and objects can contain other objects. So like if you look, this canvas is this thing. The canvas holds all of the visual elements, 2D stuff. And then inside of the canvas, there's the title. There's like a start button, and the button has some text. But in the game mode, what happens is there's a script linked to the button. So that when I press play, if you look, it says start menu. When I press play, it's going to change to game. Loaded a different scene. So in Unity, the way the user experience flows is you load and unload various pieces of your project. So you might load scenes, you might load game objects, you might load sounds. There's lots of different ways of loading things. So there's these things called asset bundles, there's addressables, there's resources, like all this jargon for basically how do you load and unload resources from the hard disk into memory. And in general, loading things from memory is expensive. And so we like to optimize by minimizing the number of times we load, or we try to load in the background so that people don't notice. So that's called asynchronous loading. We don't have to worry about that because this is a very simple project. So to bring this back to Git, if we make a change, so let's say that color of this button. So I can select an object in the hierarchy and then its settings are in the inspector. I don't like the color of this button. I want to make it red or orange or something. And now it's going to look weird because it's like purple and orange. But we've made a change. And if I save that change, Git will notice that. So if we go back to Git, we do git status, it'll say, oh, look, you changed a bunch of stuff. We need you to tell us what to do with that. So Git doesn't actually automatically track changes. You have to explicitly make them track changes. The easiest way, you can either do it like this. You can say git add assets, all this stuff. You can manually add every single file. And now one of them is tracked, the other two aren't. Or the shortcut is if you're in your root directory, you just say git add dot. The dot says git add everything recursively within this directory. And now if I do git status, it's all there. So now we've told Git to track something, it knows about it, so that if we make a commit, these things will be stored. So what you do is you say git commit, and there's a shortcut, but I'm gonna do this for now. So you say git commit. Now you have to write what's called a commit message. We're back in Vim. So commit messages, it's best if they're 50 characters or less. They should be like functionally descriptive. So that's something like, what did you change? So here, if I start trying to type though, you'll notice I can't. Oh, I did? Okay, great. Sometimes you can't. So this is called insert mode. See on the bottom left, it says insert. If I hit escape, I'm no longer in insert mode. But this is a weird version where it's okay. So if you're not in insert mode, all you do is you hit I. You hit I twice. Nope, not I twice. If you hit R, there's insert, there's replace, there's a whole bunch of things. But anyway, we want to insert. We're just gonna say we changed menu buttons color to orange. So that's good enough. And then what you do is you hit escape to leave insert mode, you hit colon to enter command mode, and you can either do X, is the shortest way, or you do right quit. And now it's saved. If that seems like a lot, it's because it is, and there's a shorter way of doing it. You can say git commit. Actually, let's make one more change. Let's say I want to change, right? Yeah, so the background color right now is actually handled by the camera. Over here, we can change, so if this is orange, maybe we want, what's blue? Okay. Or pink, purple, something yucky. It's gonna be so yucky, but that's okay. Perfect. Looks like Sesame Street. Make that change. So here's a much shorter way. So in terminal, you can chain commands. So what I'm gonna do, I'm gonna say git add everything, and this is the chaining part, and then I say git commit -m, is short for message, but I just say -m, and then I can say changed background color. I can't type that, and if I hit enter, all that stuff we did before is one line, much faster. So now we say git status, and we see that we are 2 commits ahead of the remote. Another useful tool is called git log. And now I can see all the commits that have ever been made. And I can see the origin main, origin head. Those are the branches. So those are the labels that point to specific commit IDs. So I'm gonna copy paste this commit for now. I'll come back to that. But I can do something called git reset head, this weird squiggly tilde thing. If I do two, so remember we changed 2 colors. Now check this out. Theoretically, this should have, maybe, no it didn't. Oh, okay, because it didn't, right, okay. This is not something you have to understand in detail, but if you ever have to roll back changes, now we're gonna see the colors are back to what they were. Maybe I've decided that actually I wanted the thing from before and I want to revert the reversion. If I do git log again, you'll see that those those commits look like they're missing. Let me see. Maybe I'm at the edge of what I know now, but if we do git checkout and I paste that commit from before, now I'm in, this is the detached head. Is like, so if the head is like where you are, it's not a branch, it's just where you are. It should usually coincide with the branch. When it doesn't coincide with the branch, that's called a detached head. But don't worry about that. So if you see the detached head message, it means you've been messing with Git a lot. And maybe you want to try to let's see if we can. What we're gonna do is just again git add git commit revert the revert. That's a bad commit message because what reversion? What did we do? Nothing. Oh, interesting. Okay, this is a good learning moment. So what we need to do is get back onto a branch because we're not on a branch right now. What you do is you say git checkout main. Oh, okay. Yep. We're learning. This is why it gets confused. So you will never have to do this ideally, but it's good to see it once because you should be aware that Git can be a clusterfuck. So if we do the checkout again of the detached head, what we do is we do git branch. This is going to make a new branch. We're going to call it color changes. This is sort of like our feature. Git checkout color changes. Now we're back on a branch. And if I say git log, you're going to see that main is now 2 commits behind. So we're now ahead of main, but we're no longer detached. So the changes that we've made aren't going to be lost. So now what we want to do is we want to synchronize main with our color change. So what you have to do there is we're going to do our first merge. So git checkout main. If you git log, now we're behind, so we don't see those other commits anymore. So what we do is we say if you do git branch -l, it shows you all the branches in your project. We want to merge color changes into main. So all we say, and here's something you can do. You can say git diff color changes. It shows you the difference between the 2 branches. That's a difference we approve of. We want that. So what we're going to say is git merge color changes. And now, if I do git log, main and color changes are synchronized. They're at the same commit. So finally, if we do git status, we're going to see that the origin is still behind our local. So we want other people who clone the repository to be able to see our changes. So what we have to do is we just say git push, and we could just leave it there. Git is smart enough to know that we mean origin main, but we're going to say git origin, the remote origin main. Now I have to give my passphrase again to sign the changes. And there it is. Now if we go back to this website and we go here, you can see the changes we made locally now exist in the cloud. So if any of you now pull this project, you'll have those changes. The pulling part is maybe too much because this is already a lot. But now you sort of see, you might not be able to do it, but you kind of understand the whole thing with the have these nodes, the commit IDs, and you're jumping between them. And the branches are labels for the nodes so that you can keep track. And when you merge things, it's when you're moving labels around and making new commits and all this stuff, and it's this game where you have to keep the branches synchronized, the remotes and the locals synchronized, and it is a big headache. So for instance, if we go now into source tree, we can open that project that we were just working with. I want to go one up. So this is where visualizers are really helpful. You look at the main. This is a completely linear commit history because we haven't actually made any forking. We haven't made any diversionary changes. It's all been the same. But you can go between the branches. You can see all the stuff we did. Like it's all there. So before we pushed, color changes is over here, but main would have been back here. And you can also see that color changes doesn't have the word origin in front of it. What that means is that if I go to the website and I look at code and I go to branches, color changes isn't there because we never ever synchronized it. So if we wanted to synchronize it, we would have to say git checkout color changes, and you would say git dash dash. Well, you do git set upstream origin color. If I did this right, it'll work. It probably won't. Yeah, okay, need the space. And now it says it's set up to track the remote branch. And you see that it's there. Now color changes exist. But it also doesn't need to be here, so we can just get rid of it. But we can also restore it. So on GitHub, when you delete something, you can always go into the archive. The stale branches, all branches, you can explore stuff. So like the project I was working on a couple weeks ago, let's see if it's still here. Everything got auto-updated. Right. Here we have 3 active branches. You can see that not all of them are synchronized, but if you look at all the branches that ever were, like stale, oh, nope, they're actually just gone. So they're in they are in an archive, but you just can't see them. So, but like GitHub actually keeps track of things like how many pull requests have happened, and like let's see one. So you can say I was working with one other guy, and we made 4 pull requests, and a whole bunch of things, and there's like commits and code frequency, all this, but you don't have to worry about that. So GitHub is a lot of fluff. It's all these things that help you analyze your project and like optimize your teamwork, but you don't actually need it. Nice to have, but you don't need it. The important thing is that you understand what's happening in the terminal. If you can get comfortable, either like often to start, everything we did, like you can do it in here too. You can write commit messages in source tree, and that's more comfortable, and maybe in terms of building intuition, that's a good way to start. But eventually, like if you're ever doing a real job, they're gonna want you to do it in terminal. But that involves a lot of memorization, but it's also kind of like practice. The more you do it, the more, because ideally, every time you make a breaking change, you commit that change. So you're making lots of commits every day. And so the reason, that thing called rebasing from before, not only does people stack the changes, they can squash the changes. So if I make 20 changes in a day, it might be good for me. But for other people, they just want to see what I did in one day. They don't want to see all 20. So what they do is they squash all the commits and then they rebase it. But that's like if you're working at a big company and there's a huge amount of repo and it's dozens of developers and blah, 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 blah. So for us, merging is fine. Pulling, fetching, merging, that's all you have to know. The thing with the git reset, you only need to know that if you really mess up your project and you want to go back in time to revert changes, which ideally you won't have to do, but it's good to know. And the little tilde thing means like go backwards. So head tilde 1 means go back 1 commit. But that is Git in a nutshell, and it's horrifying. So, you guys have any questions? Yes, it's the elder tour. Yeah, there's a. The problem also with Git is it was developed by lots of different people in their spare time over many years, and so there's no consistent convention to how to do anything. Like everything is a different noun and style, and but what I was thinking is how much time do we have? Yeah, time. Okay, Well, I can. Well, this is Git, but if you guys want to see a little bit of Unity, I can do that now. That way, it's not just boring.
But we
3. Okay, that's a good. Yeah.
I think that's what
Okay.
I.
Okay. Well, let's. Yeah, we can call it then. But that gives us some time. Let me just drink water. His Git Kraken. So his is called
Yeah.
Krakken. Mine is called Source Tree. They're just Git UI. Those are also helpful for things like conflicts. When you do have to deal with them, it's a lot easier if you have. Oh, for the conflicts are just hard in general. They're not. Yeah, there's a special resolve. It's called Unity YAML merge, which is like very deep in the tool chain, and you can use that to auto do it. But so something you'll learn the hard way is if two people work on the same Unity scene, there's no easy way to merge. So while you're doing experimental stuff, in the same way that you work on your own branch, you should work in your own scene. And that most of the time that's not something you'll have to worry about. And if we were really thorough, we could set up the source control. So Git is something called source control. Also plastic, there's Perforce, there's Mercurial, there's a bill. So there's Git and there's a billion other things. And those other things have different ways of handling something called binary files. Git has a hard time resolving differences between, because they're not line by line, they're bytes. And if you change one byte, that's not going to change one line. That could be the whole program. But yeah, so that thing, the smart, yeah, that's. So I've tried to set it up. I've never succeeded at setting up. Theoretically, if you get this working, you can work. So it's worth looking into, but for now, one person, one scene. Yeah. So this, and it's back. Okay. So this is a project. I kind of showed you. So you have cameras. That's like the thing that renders your world. You have lights. I can show you even. You won't work in this, but just if you want a sense of like what a large Unity project can become, this might take a moment to load. Or not, I'm not sure. Macs are cool. They've got like some things are really speedy and some. This is an M1. So it's I like it. It's an older. It's the 2020 one though. It's got the touch bar and all that.
Oh,
But like this is a much more complicated project. It's got like lights and things and it's big, crazy. And it might even have music. I don't know. I did. Well, I made it with like 6 other people. But you can. There's like talking and moving, and like the cameras are a little funky. And so that's like when projects get more complicated, they'll look like that. But for what we're doing, we're not gonna get there today. What was I thinking? So let me go back to the other one, and I'll talk a little bit about the different pieces of it, and then maybe you can try setting a very simple one up. So one thing to pay attention to is this player. Everything is gray, but then the player is blue, because the player is something called a prefab, which is like if you know what prefab housing is, it's like you order a house from a factory and it shows up all finished and you just slap it. Yeah, exactly. So it's a little bit like a little bit like having a class and making an instance of a class. Not quite what it is, but it's more like when you have when you've if you've composed an entity in a way that you like and you want to save it for later, it lets you can duplicate prefabs as many times as you want. Instead of having to like control copy paste every time you want to recycle something. The Unity's workflow is you compose entities from components, and when you have an entity you like, you save it as a prefab, and then you can reuse the prefab later. In 2019, they added something called a prefab editor, which was really nice because it used to be you couldn't isolate a prefab. You would always have to edit it in the context of a bigger scene. That's a history thing though, not something worth worrying about. But you see in the inspector, there's all these properties that you can change. So like with the spaceship, what's cool about Unity is you can change things on the fly. So right now, I have my little capsule and he does his stuff. But if you want, you can tweak things like I don't like how fast he's going. I want him to go faster. So I slide up that number on the bottom and now he goes much faster. Something maybe more impactful is there's this thing called drag. The rigid bodies are for physics simulations. Right now the drag is kind of high, so the angular drag. If I try to rotate, I stop rotating, but if I turn off angular, all of a sudden it just kind of spins forever. So you can tweak things on the fly in the editor, but the thing to know is if you don't, they don't get saved when you tweak them on the fly. So it goes back to what it was. So when you experiment in the editor, all those changes go away. So if you're making important changes, make sure you either copy them out. You can copy component properties and that sort of thing, or make your important changes when you're not in play mode. So there's the edit mode and there's the play mode. There's actually not a difference between the two of them because things like update get called in the editor and in play mode. It's just that the frequency with which they're called is different. So Unity as a runtime has the game is always running. It's just when you're in edit mode, it runs differently than when it's in play mode. But that's a behind the scenes thing that you only have to worry about if you start doing stuff like editor scripting, which is beyond the scope of. We can talk about that some other time, but there's what's really powerful in Unity is like all of these lists of properties. Like you can write your own lists and make your own tools. Unity is very customizable and extensible. But when you're just starting out, that's kind of a lot. But one thing worth doing is taking a look at how scripts are configured. I think my free trial writer has expired. I don't know. Maybe it didn't. So this is a Unity script called a mono behavior. So I don't know what the historical justification for that name is, but components in Unity are called behaviors because when you give a behavior to an object, you can compose behaviors. So some important things to note are I am namespacing this class. So a namespace is kind of like a folder or like a divider. Like if you have classes with the same name, they can collide. So it's good to have a namespace that keeps them separate. So semantically, it's good for organization. This rigid body thing, again, that's referencing the physics from before. But this colon, oh, change. That's fine. we will just ignore that. Because we're not running anything, we're just looking. That may mean my trial is expired. So in Python, you can inherit classes, kind of, on them. In C# you do that with this colon. But instead of going line by line, I should probably talk about there are these things called lifecycle hooks. So in Unity operates in discrete time steps called frames. So your computer monitor refreshes at a rate of 60 frames a second, 60 hertz. So Unity will run computations at a fixed interval of 60 times a second. Except that the interval isn't fixed, it's variable depending on how your GPU is bottlenecking. So um, the the hard thing with Unity is everything is discrete, but the period is, you don't know how quickly things will happen. So you have to take that into account using this thing called delta time, which is the amount of time between a frame, except for the fact that the physics simulation is clocked at exactly the same interval, because physics is more sensitive to regular timing than things like user input. So because we're using the physics engine, I'm using something called fixed update. But normally, if you make a new mono behavior, you're going to be presented with something called start and update. So start is this function that's called when, ooh, yes, except that there's varying stages. So at the base, when something loads for the very first time, it wakes up, awake. And once it's awake, it enables. And once it's enabled, it starts. There's 3 tiers of initialization functions. And the reason there's so many is when you have script dependencies, sometimes I need something too complicated, but when you can have different objects talking to each other, and objects have dependencies. So before I can talk to you, like before I can go to the school in the morning, I need to be dressed and have had my breakfast. Otherwise, I'm going to show up to school naked and with no food. And I'm a mess and I can't talk to you. That's not good for anyone. So what you do is when you wake up in the morning, you get yourself dressed, you take care of your own dependencies, and then you go to school. And once you're at school, you start school. When you start school, you talk to other people. So a lot of the time what happens is, like, if you look here, my awake function, I am setting up physics, basically. I need to make my behavior aware of the fact that the object it's attached to has physics capability, that it has mass, that it has velocity, all of these things. Then later on in the game, once there's more than just one object, when I need to talk to other people, that's going to go inside of start. And then the other thing is this update. So for now, you don't have to worry so much about the difference between update and fix. The difference is literally just that Unity has multiple threads. So physics is calculated parallel to everything else in the end. And it happens at a different interval than everything else. So when you do stuff related to physics, you need to make sure you're on the right. You do that with fixed update. So normally you'll use update, but in this code, everything is physics manipulation, so it's up. But that's, again, don't worry about that. Just remember that start is when you initialize, and update happens every single clock cycle. Every single time the game. Sorry? Update happens 60 times a second, approximately. So if your game lags, there's about 12 milliseconds between. Sometimes it drifts. Sometimes it's 9 seconds, sometimes it's 15 milliseconds. The important thing is that it's happening a lot, repeatedly, the exact same way every frame. So video games are about looking like they're happening consistently, but actually there's all kinds of little fluctuations where things are getting blocked and slowing down and catching up and going back and forth. Physics, the solvers for physics simulation, those are really sensitive. If they aren't regular, they can break. Things will start to fly off in random directions, gravity will break and all this. So what they do is the graphics in your game will be running at 60 frames a second, which is really pretty and smooth. But the physics will be running at 24 frames a second, 30 frames a second, because they will take the delay. They'll take delay if they can guarantee that it will happen exactly 30 times a second. So I cannot guarantee you that I can solve physics at 60 frames a second, but I can guarantee that I can solve it at 30. So they have two threads, and the physics is happening at 30, and the other thing is happening at 60. It's about stability. So graphics is less dependent on timing physics, so it's in a way more stable. So physics we have to be careful with. But again, that's just all you need to remember is if you're dealing with graphics or logic, it goes in update. If you're dealing with physics, it goes in fixed update. So the actual physics stuff here is because so in that little game with the little pill that's flying around has thrust and it has like angular thrust. It's just like a little spaceship with a little propeller at the back and it kind of turns. Um, so there's just literally all you have is you have the velocity of your rigid body and you have the angular velocity of your rigid body. And you just make contributions to those velocities and you adjust them in terms of how much time has passed between frames. That's what delta time is. It's the delta between. You have the direction of the contribution. So which arrow key am I pressing? Which way am I steering the car? And then you have these properties like thrust, which come from input. So this is where the first difficult thing, because start just happens, update just happens, but input in Unity is event driven. So what that means is the function that sets like when I press the accelerator in my car, a message, if the car is in Unity, a message gets sent to the car. One message, one discrete message gets sent to the car that I've pressed the accelerator. So update is like a continuous message. It's like a flood of messages. It happens all the time. That's not helpful. Like you could, in your update, you could say, did he press the accelerator? Did he press the accelerator? He did, great. You could do that over and over. That burns time, that burns clock cycles. So what you do is you listen. Instead, there's this thing. This is our first example of like cross-component communication. There's this player input right here. Player input has these things called events. When I press the arrow key for thrust, my player input component will talk to my spaceship controller and it invokes this function do thrust. It sends the message. So my input component, when it hears that the accelerator is pressed, sends a message to the controller saying, you better move because there's thrust now. So the threat it's event driven because an event happens and there's a response, but it's not continuous. They're not checking for the event. Respond to the event. Yes. Yeah. Yeah. There's even different. There's Unity events. There's C# events. There's delegates. But more generally, and you may have heard about this, but it's called a subscriber model, which is to say that, and this is very powerful because it lets you decouple your program. This is way beyond the scope of Unity, but it gets used a lot if you have sound and music and visuals and you want them to be able to talk to each other but not depend on each other. You decouple them using something called a subscriber pattern or an observer pattern, which is sort of like this, where you say if someone presses the accelerator, message, tell all the people who need to know that we pressed the accelerator that it got pressed. And that's other part of event driven programming is when you have the person responsible for sending the message. So like you get newsletters in your email. Anyone can get it, but not everybody does, because the only people who get it asked for it. If you ask to be updated, subscribe to an event, you can be notified that it happened. And that's for later. That's for like getting game systems to talk to each other. But events and delegates and all this, all that is just a way for one component to say to another component, please tell me when you change. So it's like a contract where you say, when you change, let me know. And that way, the advantage of that is, aside from the responsibility of the person changing, notifying everyone, the person changing doesn't have to know anything about the person they're talking to. Like when I post on Instagram, I don't know who's reading it. I'm giving you information, but I don't know who you are. Great. I don't have to know who you are. It would be exhausting to know who hundreds of people if you have hundreds of followers. But um so it's like this one to many model. And but now that you know that, um essentially that's enough to understand everything in the script. There's a little bit of vector math, like you can see there's some stuff with the dot product. That's about like when you're steering around, you have to take you need to calculate magnitudes in relation to angles, and that's blah. Um but essentially you guys sort of understand that you start up something, get ready, and during the update, you change that thing. And every once in a while, from outside, there's a shock to the system where you get a message that something changed, and then you make a discrete change in response. So if you can wrap your head around the initialization of the update, and then the messaging, you now know enough programming models to make a video game. So, and in practice, there's a lot more to it than talking about it that way, but if it's again like all this thing, it's an exercise in modeling. Can I split my game up into these little nodes? Can I describe the way the nodes need to talk to each other? Can I describe what the nodes need to do? If I can do that, I can make anything. So that's um and that's where Unity is really powerful, but it's also where Unity isn't actually, that's not a Unity thing, that's just a programming. There's other engines that I actually like more. It's just everybody uses Unity. So I have to use Unity. But you'll find if you work with it long enough that it's actually kind of it crashes a lot and it's annoying and fight with it. But the good news is you're able to learn these concepts. They apply to web programming, they apply to embedded programming, they apply to game programming. It's not just video games. It's Unity is a good way of learning lots of stuff that's valuable in other places. But that's all I have to say because you guys are probably exhausted. Yes. Hmm.
Um,
If you, all I do is for this object, I just set drag. So I give it a velocity and then I stop applying thrust, and the drag automatically slips. I don't deterministically know where the capsule's going to go. I just give it a speed. So you can, so in that game with the sheep, when the sheep jumps, it always jumps exactly 3 meters. That's because if you look, like there's a piece of code somewhere. If I go up to if I go here, go in assets, and I find the scripts, and I gotta jump. If I go into this big crazy this guy, this really really long script, there's something on the bottom called calculate, yeah, this guy, calculate jump force, and if you visit him, whatever, we'll get there. Okay, all this is physics 1 from when you were a freshman in fall. This is where physics can get a little complicated, but it's just Newtonian. It's just Newtonian mechanics, and it's not. But that, so like if you want to control specific distances,
Yeah.
you can do that, and you do it using the formulas for one-dimensional motion that you learned in. But Most of the time, you don't need to do that. Most of the time, it's good enough just to set a speed and forget it. So if you can, don't do math. Here, we're doing math because the sheep has physics and we need to make him jump a certain height. We have to, so we're doing a couple lines of math. But most of the time, don't. Don't.
What if the car?
Match speed
Yeah. In that case,
or like collisions.
yeah, yeah.
So the collisions are handled by the engine.
Oh.
And what happens is there's a message. When something collides, you get a message which has the normal of the collision and the location of the collision. Those two pieces of information are enough to let you extrapolate everything. But even the physics engine in Unity is from NVIDIA. It's not made by Unity. So, like, the thing about Unity is, like, they're kind of redundant. They make a big, messy tool that has these good pieces at the core, but there's a lot of other tools that also have those pieces. So it's a good it's good, but it's also you'll find that it's not the only solution to. But it learning it is a helpful way of. It is powerful. Roblox. Yes. Yeah. Yeah. A lot of yeah. So a lot of people, most people who make mobile games will use Unity. Most video game studios don't. If it's a big game, they won't use it. I mean, it's cool. Like they're it like yeah. I don't know. Unity has a problem to scale where the bigger it gets, the more dangerous it gets. Not a system that works well with a lot of complex projects. Unity's not so. But for what we're doing is great.
I don't think it's either.
Oh, they don't. Yep. The C++ is something you'll hear a lot about. Real, you'll hear a lot. But is it okay if I stop the recording? Then if you have questions, you can keep asking them. But just for